This presentation will introduce our newly developed Quartz transducers and their applications, entitled Enhanced Sensitivity of Quartz FM Transducer, using Double-Ended Tuning Fork for Digital Microtremor Measurement, presented at Japan Geoscience Union Meeting 2025. In this presentation, we'll focus on our newly developed M-A370 model. We'll begin with our motivation for developing this technology, then explain the sensor architecture. Next, we'll cover the specifications, followed by the practical applications. We'll then present examples of microtremor array exploration and analysis, and conclude with a summary of this work. In recent years, microtremor measurement has become crucial for assessing ground stability and seismic vulnerability. Conventional seismometers are expensive, bulky, and sensitive to electromagnetic interference. Our approach addresses these limitations through a resonant frequency shift transducer with differential configuration, followed by direct frequency to digital conversion. Our core innovation lies in the differential configuration, using 2 transducers per axis. This allows us to cancel common mode errors, such as first-order temperature and sensitivity characteristics, improving linearity and stability. Both the double-ended tuning fork resonator and the cantilever beam were made of quartz to match thermal expansion coefficients. The cantilever beam structure with a pendulum design converts acceleration to mechanical stress, resulting in the corresponding resonant frequency shift. When comparing our M-A370 with existing technologies in the market, several advantages become evident. Our quartz-based approach achieves noise density of 0.02 microGs per root hertz in the crucial 1 to 10 Hz band. We maintain an input range of ±10 Gs while delivering 0.06 microGs resolution. Digital output eliminates the need for external AD converters, simplifying system integration. This graph illustrates our sensor's noise performance. As you can see, our M-A370 blue line achieves significant improvements over our previous M-A352 model. The noise floor is sufficient to detect microtremors, well below the new high noise model threshold, approaching the performance of much heavier and more expensive sensors. The M-A370 features comprehensive specifications, optimized for microtremor measurement and seismic monitoring. Frequency range from DC to 210 Hz covers the full spectrum, needed for microtremor studies. Very stable bias repeatability, ±0.5 mg, across temperatures from -30 to 85 degrees Celsius, and ±0.1 mg at 25 degrees Celsius over a full year. Precise sensitivity characteristics, amplitude response within ±0.4 decibels, and phase response within ±0.1 degrees. Synchronization capabilities with external triggers less than 5 microseconds, and low power consumption of 37 mA at 3.3 volts. These specifications ensure reliable, long-term deployment in field conditions. Our quartz sensor technology proves valuable for structural health monitoring, where detecting subtle changes in vibration can identify deterioration before it becomes visible. Ground subsurface investigation for construction site assessment. Landslide risk monitoring in geological unstable areas. To validate performance, we conducted comparative analysis between the M-A370 and previous M-A352 models. The methodology involved double integration of acceleration data to derive displacement, application of a bandpass filter from 0.155 to 10 Hz with Hanning window. The results show excellent agreement between both sensors, with the M-A370 demonstrating superior noise characteristics. For more detailed comparison, we examine the discrepancy between the 2 sensor outputs. As for the M-A370, the amplitude of differences is less than 1 micrometer, demonstrating improved consistency between units. One of the most promising applications is microtremor array exploration. We deployed 4 sensors in a triangular array configuration to perform horizontal to vertical spectral ratio (H/V) analysis, revealing the site's resonant frequencies, to estimate a 4-layer S-wave velocity structure with these constraints. Frequency wave number (FK) analysis is also performed among frequencies from 0.1 to 40 Hz. Derivation of the phase velocity dispersion curve shows the relationship between phase velocity and frequency. Future work will include comparative studies with other sensor technologies to validate these findings. but initial results demonstrate the M-A370 is suitable for detailed microtremor array exploration. To simplify adoption, we've developed evaluation reference designs and logger software, which streamline integration. This approach allows users to connect the sensor directly to a computer via USB, visualize real-time acceleration data and perform frequency domain analysis with built-in tools, and record continuous data for later processing. For field deployments, we've created reference implementations based on the popular Raspberry Pi platform. 2 configurations are available. For the first configuration, we have a UART-based configuration, using a relay board, an evaluation board, a UART communication cable and a USB cable. For the second configuration, we have an RS422-based setup. Please note that the latest M-A370 model is not yet supported with this configuration. It includes a RS422 communication cable, a StarTech converter, and an external AC adapter. Both designs operate with Raspberry Pi, running software in Python, with data storage on a microSD card, and RTC hat for precise timing. We have developed a cost-effective solution for digital microtremor measurement. With 3-channel differential configuration for stability and linearity. Noise performance of 0.02 microGs per root hertz in the 1 to 10 Hz band, comparable to much heavier, more expensive solutions. Fully digital measurement approach, eliminating analog component limitations. Simplified deployment through direct digital interfaces and reference designs. Our future work will focus on demonstration experiments for broader applications and comparative studies with traditional sensors. We extend our sincere gratitude to Mr. Kimura and Professor Morikawa of Institute of Science Tokyo for their substantial guidance, particularly regarding the microtremor measurements at Yamakita Maruyama Park. For more information about our sensing systems and technologies, please visit our sensing system websites. Thank you for your attention.